Hello, I am Plenz, and I want to present the paper Graph Language Models, which is joint work with my supervisor Annette Frank. I want to begin with some related work on language models and knowledge graphs. If we are given a knowledge graph or a subgraph of a knowledge graph like here, which contains texts and triplets, we might want to use language models to process this, as the text information is very important and language models are very good on text. A typical approach is to first linearize the graphs, as shown here, into a set of triplets, which then the language model can process. However, the graph structure is partially lost, or at least it's more difficult to use the graph structure in this representation. That's why people also try to use graph neural networks. Graph neural networks are designed for graph structure and therefore are much better at using the graph structure. However, they are not designed to deal with textual information. A typical approach to solve this problem is to first use a language model to encode every node and then use a graph neural network on this graph with the neural embeddings. Both these approaches have their benefits and disadvantages. The language model on graph approach is very proficient in using the text data but lags behind in graph data, and vice versa for the graph neural network. Here the graph data is used well but the text lags behind. We proposed the graph language model in order to better capture both the graph structure as well as the text information inside the graphs. The idea here is that we use a graph transformer, which is a type of graph neural network and therefore capable at reasoning over graphs, and the parameters from a language model, which is pre-trained on large amounts of text and therefore very good at text understanding, to combine them in the graph language model. So the architecture, which comes from a graph transformer, brings the graph biases, while the parameters are inherited from a language model and therefore introduce text understanding. We can use this graph language model then to read in these text attributed graphs to obtain embeddings of both the nodes and the edges. Before we go into details on how the graph language model works, we need to discuss positional encodings in language models. The first transformers use so-called absolute positional encodings to inform the transformer of the structure of the data, namely here the sequence in normal text. In absolute position encodings, the tokens are simply enumerated like 0, 1, 2, 3 and so on, and then this information is passed on to the transformer. More recent work uses relative or rotary positional encodings, where instead the distance between pairs of tokens is encoded. In this work, we will use the relative or rotary positional encodings as they naturally extend to graph structured data. To use the graph language model, we first need to do some graph pre-processing. So here we again have this example graph from earlier, and the first step is that we convert all the edges to nodes and then also expand every node such that every node consists only of one token. So this triplet here, black poodle is a dog, is now represented as the sequence of 5 tokens, black poodle is a dog, which is just a normal sequence that any language model would understand. However, they're not suited to capture the whole graph structure as a whole. That's where our graph transformer architecture comes on. So how can we use positional encodings to encode the graph structure in the graph language models? For tokens which come from the same triplet, for example, all these here, black poodle is a dog, we can just use the normal relative distances because it is just a normal sequence. Same for this other triplet here, dog is a animal. However, two tokens that are not part of the same triplet, like cat is a, we cannot just use the relative distances. If we would do that, we obtain a sequence like dog is a animal, a is cat, which is not natural language-like and therefore might not work well with the inherited language model parameters. Therefore, we simply omit these connections. We do this for every token and put into such a matrix of relative positions. Here, for example, we see the relative positions for the token dog. So dog does not directly attend to cat. However, dog attends to animal and animal attends to cat. Therefore, the dog embedding will also be impacted by the embedding of cat. Previous work has found that sometimes a global view of such a graph is helpful. Therefore, we also experiment with introducing these long-range global connections. For this, we introduce a new relative distance, namely the distance graph to graph. We initialize that with the parameters from very long-range connections in the language model, which are typically small. So here's kind of an inductive bias that these long-range connections are less important, although they are accessible. This leaves us with two versions of the graph language model. We have the local graph language model, where the graph structure is used to enforce sparsity, or the global one, where the graph structure is used to introduce graph priors. We test these models on relation classification. For our first experiment, we consider constant-net subgraphs where we mask a relation, and then the task is to predict the correct relation here. We test with different subgraphs of radius r, so you have radius 1, 2, 3. And we also test with different masking, just to make the task harder and the graph structure more important. Without masking, we just have the normal graph. And then we start masking the neighboring concepts, the neighboring relations, the neighboring concepts, and so on. Our experimental setup is that we use T5 small as an encoder, so that's where we inherit our parameters from for the graph language model. And we train it for 5 runs and then average over them. We also have experiments with T5 base and T5 large, but here I want to show the results with T5 small just to allow for more baselines. The setup is that we take these graphs, we encode them with our graph language model, we take the embedding of this mask token, and on top of that we train a linear classification head, which then gives us the prediction, the relation. The only trainable parameters are in the graph language model and in the classification head. If we train both of these, we are in a normal supervised fine-tuning setting, and we also experiment with training only the classification head as a linear probe. In this setting, the graph language model's parameters come from T5, which was trained on sequences, and then we evaluate it on graphs without ever training it for any graph data. Only the classification head is trained as a linear probe. And here are our results in the linear probing setting. So when we train only the classification head, here we have the graph language model and the language model baselines where we linearize the graphs. And we see that consistently the graph language model is the best, which of course is very promising, since if it works well even without any training, it shows that the parameters in Dude work well with the novel architecture. If we mask parts of the graph, the effects get larger. So here, for example, the graph language model has a score of 41% macro F1, while the language model baselines only achieve like 20%. Again, here the graph structure is more important, so you would expect that for this the graph language model has larger benefits as it captures the graph structure better. When training the full model, so now in the full fine-tuning setting where the graph language model also gets its parameters updated, we observe something different. Namely, for small graphs, the language model baselines are actually the best, slightly outperforming the graph language model and also our other baselines. However, when the graphs get larger or when we mask parts of the graphs, so when the graph structure is more complex and more important, then the graph language model outperforms again. Here, for example, achieving 48% macro F1 compared to 40.5% macro F1 in the language model baselines. We also experiment with text-guided relation classification. So here the input to the model is a Wikidata subgraph with a aligned Wikipedia abstract. So they are, for example, on the same topic. And then the models have to reason over the text and graph jointly. So in some sense, you could say that the models have to perform relation extraction as well as knowledge graph population or link prediction at the same time using both modalities together. To incorporate such data into the graph language model, we have to again extend our relative position encodings. For the graph-to-graph attentions, we have the same layout as before, and for text-to-text, we just use the normal ones as any normal sequence transformer would use it. And for the cross-modal connections, so from graph to text, we introduce again novel relative positions for the graph to text and for the text to graph connections. These new relative positions allow the model to learn how much each modality should attend to the other one. When we conduct an ablation on the graph language model, we see that the model performs best when both the text and graph data is available, while the text and graph data contribute roughly the same amounts. So the model really seems to be using both modalities. In conclusion, we propose two novel graph language models, namely the local and the global one, and they performed strong baselines both without any training of the graph language model parameters and also when being fine-tuned, both on constant-net as well as in the setting where we have Wikidata and Wikipedia abstracts. If you like this work, please feel free to stop by our poster or talk to me anytime at the ACL. Looking forward to seeing you all, and thank you very much.